All right, I'm looking at problem number 19, the one regarding fraudulent credit card charges. And what we want to do is we want to determine first whether or not we can use a normal distribution to approximate the binomial distribution. And then if so, we want to use that normal distribution to approximate the indicated probability. Now, you could definitely easily answer this more accurately using the binomial distribution and using technology. Okay, but again, under a lot of situations, the binomial distribution can be approximated by the normal distribution. And we will use that property later in the course when we cover confidence intervals for proportion and hypothesis tests for proportion. So it's good to be familiar with this property. All right, so we're told that 41% of U.S. adults have encountered fraudulent charges on their credit cards. All right, so you randomly select 100 U.S. adults, and we want to find the probability that the number who have encountered fraudulent charges on their credit cards is A, exactly 40, B, at least 40, and C, fewer than 40. So the first part of this problem was asking, can we use the normal approximation to the binomial to begin with? So we want to know, is n times p at least 5 and n times q at least 5? All right, if those two conditions are met, then we have a normal distribution. All right, so we have a normal distribution. Approximately, this is an approximation, with mu equal to n times p. All right, that's the mean we saw from the binomial distribution. And sigma is equal to the square root of n times p times q. Now, these are the two parameters, mu and sigma, that we need to use the normal distribution. Okay, so we're given that p is equal to 0.41. Okay, it said that 41% of U.S. adults have encountered fraudulent charges on their credit cards. So that forces q, which is 1 minus p, to be 0.59. And in this problem, the sample size was 100. All right, so we first want to find out, is n times p at least 5 and n times q at least 5. So is 100 times 0.41, is that at least 5? Well, yes, that would be 41. 41 is at least 5, and is 100 times 0.59, is that at least 5? That would be 59, and that is at least 5. So yes, the conditions are met to use the normal approximation to the binomial distribution. So the next step is to find mu and sigma. So we can use mu and sigma to use the normal distribution. All right, so again, mu is equal to n times p, and sigma is equal to the square root of n times p times q. So we need mu. Mu will be equal to n times p. So that's going to be equal to 100 times 0.41. So that's equal to 41. And we're going to need sigma. So sigma is equal to the square root of n times p times q. So sigma will be equal to the square root of 100 times 0.41 times 0.59, all under the radical. And if you're playing along with your calculator, that's approximately 4.918. I went ahead and rounded to 3 decimal places. Okay, so now we know we have a bell-shaped distribution with this mean and this standard deviation. So now this problem essentially reduces to section 5.3 5.2, the non-standard normal distribution. However, we need to account for that continuity correction. All right, so for part A, we're asked to find the probability that the number who have encountered fraudulent charges on their credit cards is exactly 40. So we want to find the probability X is exactly equal to 40. Now remember, and I went over this in my last video, okay, I'll try to do a little mini sketch off to the side. Okay, so we have a bell-shaped distribution, and let's say 40 is up here. Remember, the number 40 in the continuous case is expressed as 39.5, up to 40.5. So using the continuity correction, okay, the CC, that's going to be equal to the probability X falls between 39.5 and 40.5. I'm getting a little squished here. Okay, so from this step right here, we could go ahead and we could either standardize each of these endpoints. In other words, we can convert to z-scores and use the z-table, or you could go ahead and use the TI-84, which is what I did. Okay, so in the calculator, I use the normal CDF. Normal CDF. At this point in time, you should be familiar with this function and where to find it. Okay, my lower bound was 39.5, my upper bound was 40.5. Okay, so on the calculator, just to review, we want to go to distribution, and I want to go to the normal CDF. Whoops, shows the wrong one, excuse me. And get out of there. All right, so stat, oops, wrong button again. Okay, so distribution, normal CDF, my lower bound is 39.5, my upper bound is 40.5. Now, I'm not working with standard normal. Okay, I found that mean. The mean is 41 and the standard deviation is 4.98. Okay, so 41. And sigma is 4.918. And then finding that probability, we get about 0.0793. Okay, so for grins and giggles, you could go back to the binomial distribution and actually find that probability a little bit more accurately using N and P. Under the binomial PDF function if you want to. Okay, so part B asks for the probability that the number who have encountered fraudulent charges on their credit card is at least 40. So in probability notation, the probability X is at least 40 would be X greater than 40. Okay, that greater than or equal to, at least includes the case of equality. So again, because we're including 40 and looking at the sketch here, the number 40 in the continuous case will go down from 39.5, and if we're greater than that, greater than or equal to, we're going to go to positive infinity. So first, using that continuity correction, I'm going to rewrite that as the probability X is greater than or equal to 39.5. Okay, so here's my lower bound for the normal distribution. My upper bound is theoretically positive infinity. Okay, and again, we're going to be using mu and sigma that we found, 41 and 4.918 respectively. So going back to my distribution menu, going back to normal CDF, my calculator has saved the previous information, but I want to change this upper bound to a very large number, so one with a bunch of zeros, and I can leave mu and sigma alone. And then after entering, I get a probability of about 0.6198. Again, you want to round however you were told to round in the homework. All right. And then the last part was finding the probability x is fewer than 40. Okay, so that does not include the 40. So in probability with inequality notation, that's going to be the probability x is less than 40. Fewer than 40 does not include the 40. Looking at our little mini picture here, if I'm not including the 40, and 40 actually starts at 39.5 in the continuous case, I'm looking at the area completely to the left of 39.5. So applying that continuity correction, the CC, that's going to be equal to the probability x is less than 39.5. Now, in the case of in the continuous case, it doesn't matter if you can include the case of equality or not. All right, so again, I can use my normal CDF function in the calculator. So I'm going back to my distribution menu, select normal CDF. Now this time my lower bound is a very small number, so I'm going to put a -1 and a bunch of zeros. My upper bound this time is 39.5. Mu and sigma are the same. And entering through that, I would get about 0.308, okay, rounding to 4. Okay, just for comparison, let's look at part C, but this time we'll treat it as strictly binomial. Okay, under the binomial case, the probability x is less than 40 does not include the 40. So in the binomial distribution, we would be finding the probability x is less than or equal to 39. So going to my distribution menu and scrolling down to binomial CDF, because I'm finding a less than probability, I have 100 trials. My probability of success is 0.41, and my x value is 39. Okay, because if I'm sticking with the binomial case, x less than 40 does not include the 40. So if you recall from section 4.2, the section that covers the binomial distribution, we would have to stop at x is less than or equal to 39. All right, so let's go ahead and put that in. And for comparison, the probability isn't identical, but it's pretty close. If we rounded to the nearest hundredth, it would look the same. So this is what they mean when they say this is a normal approximation to the binomial distribution. And if we increase the sample size, we would get a better approximation. So I hope this helps you work the homework problems in this section. All right, looking at this probability expression as a binomial probability, this would be the probability x is less than 25. That does not include the 25. So if we were using the binomial distribution, in particular the binomial CDF on your calculator, we would be finding the probability x is less than or equal to 24. However, under most conditions, the binomial distribution can be approximated by the normal distribution. However, the binomial distribution is a discrete probability distribution, and the normal distribution is a continuous probability distribution. So we need to account for that. So this expression here is the probability x is less than 25. So applying the continuity correction here, since it does not include the 25, this would be the probability x is less than or equal to 24.5. Okay, so visually, what that means is I'm assuming that this binomial distribution can be approximated by the normal distribution, so I'm just going to draw a generic bell curve. So the number 25 in the continuous case actually is represented by adding 0.5 above and subtracting 0.5 below. So the number 25 is this area here in the continuous case. So going back up here, if I'm not including the 25, then I need to stop at 24.5. Okay, so let's go ahead and do some conversions between discrete and continuous, and hopefully this will help you with your homework. Okay, so I'm going to use the number 25 for x in this situation. All right, so if x is equal to 25, okay, the case of equality, right, so this is equal. What that means is I want to find the area in the continuous case between 24.5 and 25.5. So in the continuous case, that can be represented as this inequality. 24.5 is less than or equal to x is less than or equal to 25.5. All right, so if x is greater than 25, all right, that would be greater than, sorry, I'm writing a little small here, greater than. That does not include the 25, so looking back at our sketch, that would be the area that goes from 25.5 to positive infinity. So as expressed in inequality notation, this would be the probability, actually I'm not going to use probability, I'll just keep it as inequality. Okay, the corresponding inequality would be x is greater than or equal to 25.5. Now, for the case where x is greater than or equal to 25, okay, now we have the case of equality. So this is greater than or equal to. We are now including the number 25. Now remember, 25 in the continuous case goes from 24.5 up to 25.5. So if we want to be greater than 25, greater than or equal to 25, we would need to go down from 24.5 up to positive infinity. So in the continuous case, that would be x is greater than or equal to 24.5. Now for x less than 25, okay, so we've got less than. Again, that does not include the case of equality, and that's the one I started with up here. Okay, if I'm not including the number 25, and remember 25 in the continuous case goes from 24.5 up to 25.5. If we're not including 25, then we would be looking at everything below 24.5. Okay, so that's x less than 24.5. All right, and then last but not least, we could have x less than or equal to 25. Okay, so that would be less than or equal to, okay, less than or equal to 25. Now we're including the case of equality. So we want to include the whole number 25, but in the continuous case, 25 goes all the way up to 25.5. So in the continuous case, as in an inequality, that would be expressed as x is less than or equal to 25.5. Okay, so this is the first step of these probability problems, and in the next video we will do a whole problem where we first convert using the continuity correction factor, then find the corresponding mean and standard deviation, and then find the probability using the normal distribution.